Continuous? No way. A function is continuous if you can draw it without lifting your pen. By that rule, this one isn't continuous. But why this famous pen rule is only half the truth, and what the cooler mathematical version looks like, you will see now. Let's look at this function and ask whether it is continuous at the point x0. The concise general definition says a function f is continuous at x0 if the limit of f of x as x approaches x0 equals f of x0. So, as I get closer to the point x0, the function value must also get closer to f of x0. This should hold whether I approach from the left or the right. That's why, for real functions, continuity is often checked using the left hand and the right hand limits. In this case, if both the left hand limit and the right hand limit exist, are equal, and match the function value f of x0, then the function is continuous at x0. However, this view only really makes sense for one-dimensional functions, because left and right exist only on the real number line. But this general formulation automatically covers this. In other words, small changes in x near x0 produce only small changes in the function values at that point. For example, this would not hold for a function like this at x0. Here, the right-hand limit satisfies the condition, but the left-hand limit does not. No matter how close I get to x0, the function value stays at a different level and does not match f of x0. So this general condition is not satisfied. As simple as the limit definition is, mathematicians like to write it more formally. That's where the Epsilon-Delta criterion comes in. Let's again consider a function from a domain D to the real numbers. This function is continuous at the point x0, that means any point in the domain D, if for every epsilon greater than 0, there exists a delta greater than 0 such that the following condition holds for all x. If the absolute value of x minus x0 is less than delta, then the absolute value of f of x minus f of x0 is less than epsilon. Okay, let's make this visual. This means that for an epsilon neighborhood around f of x0, there exists a corresponding delta neighborhood around x0. For all x in this delta neighborhood, the absolute difference in function values is less than epsilon. If epsilon is chosen smaller, delta, which depends on epsilon, is adjusted accordingly. If this holds for every epsilon greater than 0, no matter how small, then the function is continuous at x0. So this implication says the distance between f of x and f of x0 is guaranteed to be smaller than epsilon whenever the distance between x and x0 is smaller than delta. This definition of continuity is thus equivalent to the limit definition we mentioned before. Essentially, it formalizes what the limit expresses. X approaches x0, so the distance gets smaller. F of x approaches f of x0, so the difference in function values gets smaller. When we say generally that a function is continuous, we mean that it is continuous on its entire domain. That is, f is continuous at every point of D. That means for every x0 in the domain. Let's look at this function again. We already said it is not continuous at x0. This becomes clear visually if we place a small epsilon tube around f of x0. We cannot find a delta interval around x0 where all function values stay within epsilon of f of x0. For example, if we pick this specific delta, there exists an x such that the absolute value of f of x minus f of x0 is greater than epsilon. The same goes for this delta, and so on. In this case, we apply the negation of the epsilon-delta condition to show that the function is not continuous at x0. The negation says there exists an epsilon such that for every delta there is an x with the absolute value of f of x minus f of x0 greater or equal than epsilon. And that's exactly what we see here. So this function is not continuous at x0. Note, a function can be continuous on parts of its domain, But if it is not continuous at every point in the domain, it is considered overall discontinuous. Okay, let's go through with some numbers. We consider two functions and want to check continuity at x0 equals 4. First, let's check the case where the two-sided limit exists and equal the function value. For the left function, whether approaching from the left or right, the result is 2. So the left hand and right hand limits match and equal the function value f of x0. It is continuous at point 4. On the right, the situation is different. While the right hand condition is satisfied, the left hand limit is not. The left hand and the right hand limits do not match. The function is not continuous at 4. Now let's look at it with the Epsilon-Delta criterion. Consider approaching the condition from the right. We want the absolute value of f of x minus f of x0 to be less than epsilon. So let's write it down to make it less than epsilon and see what the corresponding delta must be. The absolute value of f of x minus f of 4. Now we can plug in the function, factor out the 1/2, and then we see that this must be less than delta. Now by choosing delta equals 2 times epsilon, the condition is satisfied. Here we set delta to be 2 times epsilon and see that the condition is always satisfied. Often the delta dependence on epsilon is fixed before starting the proof. Then we could phrase it like this. To make the absolute difference between f of x and f of x0 less than epsilon, it seems suitable to choose delta equal to epsilon. One could also choose, for example, delta equals 1/2 times epsilon. The condition would still hold. So, for every epsilon greater than 0, no matter how small, there exists a delta, in this case maybe twice as big as epsilon, such that the condition is satisfied for all x. The function is continuous at x0 equals 4. For the right function, continuity at x equals 4 would require the same. But if we take, for example, epsilon equals 1/2, we see that there is always an x in any delta interval such that the absolute value of f of x minus f of x0 is not smaller than epsilon. No matter how close we get to 4 from the right, the function value is at least 3. So the difference with f of x0 is always greater than 1, which is certainly larger than epsilon. Here we applied the negation from before. There exists an epsilon such that for all delta, an x exists with the absolute value of f of x minus f of x0 greater than or equal to epsilon. Therefore, the function is not continuous at 4. So why doesn't the draw without lifting your pen rule always work? Consider, for example, the function f of x equals 1 divided by x on the real numbers excluding 0. This function is continuous on its entire domain, since we don't include 0. Yet, its graph consists of 2 separate parts. That means I have to lift my pen in order to draw this function. So, continuity is thus not about drawing, but a property relative to the domain.